So, and that's let's do here. Okay, so a warning before starting to talk about the blockchain. So as I said before, I won't talk about the philosophy. I won't talk about ICOs, you know, expressions like to the moon or whatever. I won't even recommend you to invest in any cryptocurrencies or altcoin or whatever. I'm not into speculation anyway, so it's not that interesting to me. But as a developer, I like to understand the concepts and the technologies behind new trends. So the thing is, I want to know if a blockchain can be useful to solve some problems that I might have for my projects. Is it something that is useful? What kind of problems does it solve? Why does it work? That's the kind of questions I'm interested in. So mostly from a technical standpoint. And of course, it looks like the blockchain is going to solve all the problems of the world, right? Almost all of them. There are so many new projects out there with a blockchain somewhere. So it looks like we've just discovered a magical technology, a magic wand that would, you know, solve any problems out there. And it sounds like a déjà vu. A few years back, it was all about NoSQL databases, for instance. They would solve all the problems, right? How many of you are still using NoSQL databases? MongoDB, for instance. Okay, so it does not solve all problems, obviously. So having something that can solve anything, it makes me skeptical, I would say. So I want to understand why people are so excited about the blockchain. And I wanted to be able to realize for myself if it's something interesting or not, if it would be a good fit or not. And of course, you should always use the right tool for what you are doing. And before going further, I'm going to tell you what I'm thinking about the blockchain and my take on that. The concepts, as you will see, are quite easily understandable. They are quite simple and powerful, really. But the blockchain was created to solve a very specific use case. And if you do have that specific use case, then a blockchain is probably something you might want to use. But the reality is that almost no projects need a blockchain. And boring and, proven technologies are almost always better than using a blockchain. So if you are interested in finding ways to use a blockchain, I won't tell you anything about that because I have no ideas why it would be useful outside of the main use case. Okay, now let's talk about digital money because of course blockchain is, or a blockchain or blockchains, I don't know how to say that. Blockchain seems kind of weird, I would say. It all started in 1989 with DigiCash. It was the very first digital money. And I think it went bankrupt 10 years after that, so in 1998, 20 years ago. It was kind of interesting as an experiment. Of course, nobody was, it was not useful because it was not really accepted anywhere. I think one US bank actually supported this digital money, but that was all. But it was interesting, at least for something, because the day the company disappeared, the money was gone as well, right? Which is kind of not that great, really. So more recently, Bitcoin, and I suppose all of you are aware of what Bitcoin is. Yeah? more or less. That's a speculation tool, basically, right? That's a digital money, coins. And the white paper was published 10 years ago in 2008. And basically, the Bitcoin is not about something that is really new or different from what we had before, but it is really just about a few things put together, and it makes the Bitcoin system really powerful. So the first one is identity, and we're going to talk about that, decentralized network, and consensus. And the last one is the most important one. I highly recommend you to actually read the white paper. It's only 8 pages long, so it's really short. It's really easy to understand what's going on in the paper, and hopefully after the talk, it's going to be even more easier to understand. Okay, so the first step here is I want to create a digital money really quickly so that we can understand what we're talking about. So I'm going to switch to some code now. So that's my take on digital money in PHP. So it's quite short. Basically, we're going to use HTTP, and we are going to store the state of the balances in a file. So this file is going to include all the balances of the users of the system. So if it does not exist yet, we initialize the database with one user, me, and let's say that I have 1 million Fabcoin, right? So the money is actually the Fabcoin. Okay, so now what we can do, 3 different things. The first one is we can get a balance for a user. We can create new users, and by default they have 0 Fabcoin, of course. And then we can transfer money from someone to someone else, and we give the amount. And of course, if the amount is more than what you have, you can't transfer the money. That makes sense, right? And then we do some math operations here, and we save into the balances. So basically, we have one central server, my laptop here, and you can call some HTTP method to do things. So let's try that. So first, let me use the PHP built-in server.
Can you make it bigger?
Sure. Is it better? Yeah. So first, let's have a look at the balance for me. So I have no coins. Really? Oh, sorry. So for user Fabian, so I have a bunch of coins. Let's create a user. So we're gonna submit a form. Who wants some Fab coins? Wow. Okay. What's your name?
John.
John. Like this? Like this?
Yeah.
Okay. Okay, how many coins do you have?
2 million.
No, 0. Do you want some?
Yes.
Okay. Fair enough. Let's do that. Transfer some of my coins. So from me to you. How many do you want?
2.
2?
I get you a coffee, you give me the coins.
Okay. Okay, here you go. You have 2 coins. We do have some money, right? Cool. Can you see some problems? Anyone? No history. Okay, that's fair. No history.
It's a central server.
Yeah, exactly. Centralized server, and that's a problem. Why?
Because it could get hacked.
Yeah, sure, and I can shut it down, right? Or the government can shut it down. And trust.
Or I
Why trust?
have to trust the one safe
You can trust me, right?
Absolutely.
Okay. Yeah.
I'm just saying, I can have another copy of your server, and I said, John has 20 coins,
Uh-huh. Yeah,
who's right?
exactly. Yeah, sure.
Can you repeat the comments for the recording?
Okay, sorry. So there are a bunch of problems. I'm going to recap all the problems anyway, because you almost got all of them. So the first one is, so I think the first problem is that there is no blockchains. It's not interesting. No blockchains. That's the very first problem. The second one is, of course, availability. If I shut down my server, no coins anymore. And we cannot transact anymore. So I cannot send coins, and nobody can actually use the money anymore. That's a problem. The authentication, of course, because I can steal your coins really easily. There is no authentication. We could add some kind of passwords or something like that. That could work. And security, of course, because if someone is able to hack my laptop or server or whatever, then he can steal some money. He can print new money if he wants to. That's also a problem. And trust, you cannot trust me, really. I would not trust me. It's so easy to actually abuse that power really easily. So the first thing I want to talk about is how we can actually fix availability. So we don't want a single point of failure. We don't want one central server. We don't want a central bank, actually. So decentralization is one way to do that, and that's what was missing with DigiCash. They had a central server, and we will understand why in a bit, which means that when they shut down all the servers, the money was gone. So what we want is we want a web of servers, so many servers that are participating in a network, and we want to do that in a resilient way. We want to be able to join or leave the network without any impact on the network. So we need at least one server, of course. If we shut down the last server, it's gone. But if we have at least one server, the network can leave. So to do that, we need also a protocol so that the servers can actually talk to each other, right? So that we can transfer the money, we can create users, and we have a shared state between all the servers. We can't use a client-server protocol, of course, because it means a central server. So what we want is, for instance, a gossip protocol. So a gossip protocol is when everybody can talk to each other, basically, which means that nobody is actually controlling the network. Everybody talks to each other, and that's how we can decide the state of the system. And instead of having one computer or one cluster of servers having the state, everybody has all the information about the system. That's how it works. So to get started, you don't have one address. You need to know at least one node on the network to be able to connect. And then we propagate the information. So I'm going to connect to John, and John knows about Larry, and Larry is going to give me his node address, and we are going to communicate like that, right? So we can discover the topology of the network quite easily like that. Okay, so to understand the gossip protocol, we're going to forget about the money for a minute, and I'm going to take another example. Let's say that we want to share our best session at DrupalCon, right? Mine is about, I don't know, a session about Twig. And John, as you like the session about Symfony, right? Yes, of course. But you can change your mind. So let's say that, quite randomly at some point you decide that you don't like the Symfony session that much, and the session about Drupal 10 was much more interesting. So, and we want to propagate that information on the network. Okay? Okay, so the thing is, every few seconds I'm going to talk to all the nodes I know, I'm aware of, sending my state. And in return, you're going to first update your state and send me back your state. And that's how I'm going to be aware of what's going on in the network. And as you can imagine, it can take time to actually propagate the information, right? Before I know about the best session from some guys over there, it's going to take time to propagate in the room so that I get the information. So that I can also update my own state. So let's see how we can do that in PHP. Gossip protocol. Okay, so we have a state. That's where I'm going to store all the information about the sessions that we like. So the first thing is, when we create the server, I need to know my port. That's the address where you can join me, contact me actually. And then I need also a peer port, and that's one node in the system so that we can connect to each other. So the very first one, we don't have the peer port, of course, because we need to bootstrap the network. And then we have a loop here, and we are continuously checking all the ports that we are aware of. So at first, that's only one port, and we are contacting the node sending our state. So the state is a simple array with the username, the session, and the version. Why do we need a version here? Let's say that John said that his best session was about Symfony. But then, 2 seconds later, he decides that it's not Symfony anymore, it's Twig. But he can say Twig to me, he said Symfony to Larry, and then Larry said, oh, John said that Symfony is the best session, and now I have two pieces of information. The first one is, you like Twig, it was true 10 minutes ago, it's not anymore, and Larry told me that now it's Symfony. So I need to decide the order of the messages, right? So if you had a version, then if Twig is version 1 and Symfony is version 2, I know that I can discard Twig version 1, and the current best session for you is Symfony. So that's why we need a version here. So we are sending all the information about all the nodes we are aware of to all the nodes we talk to via HTTP. In return, the peer sends the state that he has locally, and we update our state based on that information. So how do we do that? So update is about getting all the state, so for each port, the data that they have. That's my port. You won't be able to update my data, so just ignore that. And then, so here, this is just to check that the data is valid, actually. And then, if I know nothing about you, then I'm going to trust the data that you are sending to me. And if I already have something, I'm only updating the data if the version is more than what I already have in my state, right? Okay, and after doing that with all the nodes, randomly, or not really randomly, well, at least, yeah, randomly, I'm going to update the best session. That's all there is to it, really. Let's see how that works. So here I have different sessions. I'm going to make it a bit bigger. Okay, so, I also have a script here. It takes a user, and based on the user environment variable, we create a small PHP built-in server, and we try to find an available port so that people can connect to us. Okay, so here I'm saying the user is Fabian, and I'm running the gossip protocol like this. Not really. So as you can see, now I'm only aware of my own best session, and you can see that from randomly I'm updating the session I like the most. To join the network, I need to create another user, Ellen for instance, and I give it a peer. There is only one, Fabian, and I'm going to run the gossip protocol as well. And you can see that they are starting to talk to each other, right? So, and you can see that at some point they reach a consensus and they have the exact same information. But that's not always the case, because it takes time for the information to propagate over the network. And we can create another one. Thomas is going to connect to Ellen, so this node knows nothing about the first node, but just because we are propagating the information, at some point is going to be aware of all the nodes, and as you can see, everybody is talking to each other now, updating the best session over time. So that's the gossip protocol, which means that I can kill any node. It does not matter. It still works. I can join again, and I'm going to catch up really quickly, right? Okay, so that's the gossip protocol. Okay, so we have achieved something very important, which is fault tolerance. I can, a server can go down, it doesn't matter, anyone can join and leave and join again, that's not a problem. But there is a problem here. Someone can lie. Okay? If you tell me that Larry's best session is Twig, and you put a version number that is really high, I'm going to trust you. But actually, Larry doesn't like Twig that much. So how can we fix that? The problem here is that we don't have the notion of an identity, right? So we need to fix that. And the problem with the gossip protocol and the fact that the state is shared amongst us, we cannot have passwords. I cannot send you the password, my password. That would not make sense. So we need something else. And something else is cryptographic identities, or a public key and a private key. Basically, the public key is the equivalent of a username, so you can give it to all the peers, all the nodes in the network. That doesn't matter. And the private key is the equivalent of the password. So that's a secret. You should never ever share the password, the private key. But the big difference between a username and password and public key and a private key is that the public key and the private key are actually connected. They are related, right? There is a link between the public key and the private key. You can't change the private key without changing the public key, right? So your identity on the network is made of your public key and the private key. You keep the private key private or secret, and you can give the public key to anyone. And the great thing about the public key is that it says nothing about you, right? There is no tag attached to that. So it's not Larry, it's not John, it's not Nicholas, it's not Thomas, it's just a random series of bits, really. So the thing is, with the private key, what you can do is you can sign messages, you can encrypt messages, and that's the key here. When someone sends an information, a message, he signs the message with his private key. And he can also attach his public key. And then with the public key, I can check that the message actually comes from the person who actually owns the public key, which means that now the messages cannot be forged anymore, right? Because if you don't have my private key, you can't fake a message with my public key, even if you do have the public key, right? So let's see how that works. I think it's going to be much clearer with an example. Okay, so I'm going to use PHP again. using OpenSSL for doing the work. So the first function I have here is a generate key pair method. And basically, we are using OpenSSL to create that, and we return the private key and the public key. Let's try that. And then I have three more methods. The first one is encrypting a message. So we give it a message, which is basically a string. We give it a private key. We are using OpenSSL to encrypt the message. We get back the encrypted message. And we are using base 64 encode because, when you encrypt something, you get back a random bits. So if we want to print that, we need to convert that to something that is more readable, and base 64 encode does the work. If we have the public key and an encrypted message, we can decrypt the message, and validating the message is as simple as you have the message in clear, and we don't care about the fact that the message is in clear. Here we have the encrypted message, and if we decrypt the message and it's the same as the original message, we know that this is valid, right? So here in the example, let's do it like this first. So I'm going to create a key pair of public and private keys. I have a message, hello Drupal, and I'm going to encrypt the message with the private key. Okay. So here what you can see is the encrypted version of the hello Drupal message. If I know your public key, I can decrypt the message back, and you can see that it's hello world. But more interesting is that you can also check if it is valid. Valid means that I know that the message was actually encrypted with the private key related to the public key, right? And that's what I'm interested in here. Okay, so next step. So so that's the way we can be sure that you can't lie about your best or favorite session. But the problem now is that I can send, I'm going to use Bob and Alice. That's going to be better. I'm going to send Bob a message, encrypted message, that Twig is my favorite session, so he can check that I've actually sent a message, and I'm going to send another information like Symfony to Alice. So Bob and Alice, they can check that I am the one who actually sent the message, but the messages are different. For sessions at DrupalCon, that's not really a problem, but if we are using money now, that's a problem. Let's say I have a coin, and the coin is actually a message. And I send a coin to Bob. And I want to send the same coin to Alice as well. Both of them, they will be able to check that I am the owner of the coin. I have signed a message, but I have actually spent the same coin twice. That's a problem, right? So we need to be able to solve that problem. And that's the hardest problem to solve for cryptocurrencies. And that's where Bitcoin actually solved the problem quite elegantly. Okay, so so the thing is, and of course, I've sent the coin twice, and I got back something in return, right? A book or whatever, a car, whatever. But the thing is, now Alice wants to spend the coin again to buy something else. And at this point, she's going to realize that the coin actually belongs to Bob, right? And there is nothing she can do. So the thing is, if at some point Bob and Alice, if they were able to talk together, they would have realized that the coin was actually sent twice, right? And that's only possible if they had waited a lot of time. Just waiting is enough. Remember, with the gossip protocol and network, it takes time for the information to actually go from one node to all the network, right? So if they can wait enough, they would have both the information that the coin had been spent twice, right? So in a peer-to-peer network, can we solve what we call the double spend issue? The first one, the first possibility is coordination, exactly what I've just talked about. Coordination is we wait enough so that we have all the same state, and when we have all the same state, we can know that there is a problem in the network, and then we can resolve the problem. So basically, we want to know if I sent the coin to Alice first or to Bob first. If it is Alice, then the Bob transaction can be discarded, and the other way around. Okay, so coordination. How can we do that? The solution of Bitcoin is what we call proof of work. So we need to wait for the information to propagate, or put another way, we need to slow things down. We don't want to have things going too fast. So instead of being able to say, okay, I've sent you the coin, transaction done, we need to wait. We need to slow things down. So to do that, we're going to use what we call proof of work. And the idea is that when you send a message, you need to actually do some computational work. You need to do some work with your CPU. And a CPU can resolve math problems, so we give you a math problem to resolve. But before to talk about that, I'm going to show you something. It's going to be much easier to understand after that. Let's say that I have my message again, hello world, hello Drupal, and we are going to use a hash function. A hash function is something that takes an input, gives you an output. For the same input, you are always going to have the same output. And the great thing about hash functions is that if you change slightly the input, the output is totally different, and you can't go back. If you have the output, you can't go back to the input, right? So let's see how that works. So in PHP, you can use the hash function, and I'm going to create the hash for the message. Okay, that's a hash, right? Random bits, really. If I slightly change the message here, you can see that all the bits are different. And there is no way I can go back to the string. First, because we can't encode all the information. Even if the string is really, really, really long, the hash is always the same size, right? So you can't, it's not encryption. It's really just a hash. And whenever you give me the same input, you're going to have the same output. As you can see, computing a hash is really fast. So that's not enough. So the problem to solve here is, can you find something to add at the end here so that the hash starts with a certain number of zeros? So let's say that I want 1 0 at first. So I can try it with, I don't know, A. Does that work? That doesn't work. B. Does that work? That doesn't work. C. Okay, I can do that all day long, right? So it's something that is intensive, CPU intensive, because you need to try a lot of different possibilities to actually find a solution. So that's the puzzle that is behind the Bitcoin mining process actually. So here we want to find a nonce. A nonce is really just a random string for a message. So the nonce here is an integer. We are iterating and adding one for each loop until we find a valid nonce. And a valid nonce is just a hash starting with 1 0, for instance. Let's try that. Okay, and I need to print the hash to be sure that it worked. Okay, so we needed 25 iterations to get 1 0 at the beginning of the hash. Now, if I'm adding more zeros, it's exponential. So if I say I want 4 zeros, it's going to take much more time, right? And if I want 5 of them, and if I want 6 of them, it's not going to work. It's going to take a lot of time, right? That's the complexity of the puzzle. And in the Bitcoin protocol, the complexity is automatically adjusted depending on the number of nodes in the network. Right? We're going to talk about that a bit later. So that's the proof of work. Very simple one. You give me a message. I want to slow things down, so you need to prove that you spend some CPU time to actually compute the hash because you need to have X zeros at the beginning of the hash string. Okay, so that's what is called mining in the Bitcoin protocol, just because you are doing some work to get some gold or Bitcoins. But that's not enough. I can still send the same message, even if I spend a lot of time doing the mining. I can still send Bob and Alice the exact same message, and I can also sign the message. So what is missing here is the order of the transactions. I want to know that I did Alice before Bob. And I want to be sure that when I know that Alice was first and Bob after, I don't want someone to be able to say, no, it's Bob first and then Alice. So I don't want someone to be able to change the order after the fact. So to do that, we need a blockchain at last. That's the problem we want to solve with a blockchain. So a block is the message you want to send to someone, to the network, plus the hash. We've just talked about the hash. So the hash is actually computed with the proof of work algorithm, so it takes time to compute. And then we also have the previous hash of the previous block, right? So when I'm computing the hash for block number 2, I'm going to find a hash that is made of the message plus the previous hash, right? Which means that after I have added block 2, I know for sure that block 1 is before block 2 because I have this relationship between block 1 and 2. Yeah? Is it clear enough? So we cannot shuffle the blocks anymore. If we shuffle the blocks, it's not valid anymore. The hash is not going to be valid anymore because the previous one is not going to be the right one. And basically, that's a blockchain. A blockchain is a linked list with hashes. Nothing more. It does nothing. It solves no problems whatsoever. And no, a blockchain is not a database. It's not a distributed database because remember, all the nodes on the network, they have the state, the entire state, the history, right? So that's very different from a database, actually. Oh, sorry. Okay. But still, it's not enough. The blockchain, like I've just talked about, it's not enough to have all the things that we wanted for our Fabcoin cryptocurrencies. Because what I can do is, well, first, perhaps we can have a look at how to implement a blockchain. Let's see how we can do that. Okay, so I have my proof of work class. This is exactly the same as before. I have a block. A block is a message and the previous block, right? In the block, I'm going to keep the previous hash of the previous block, the message, and I'm going to mine the block. That's where I'm going to spend some CPU time. And here I want to find a nonce for the message plus the previous hash of the previous block, which means that if I want to replace the block, I need to redo the work of all the blocks after the block I want to mine. And then I'm going to store the nonce, I'm going to store the hash. Something very important, I need to have an isValid method so that I can check that the block is valid. And the block is valid if the nonce actually has enough zero for the message that I want to encode. Okay? Now the blockchain is an array in PHP of blocks. Pretty simple. When we create a new blockchain, we initialize it with one message and no previous block. And then when we want to add a message to the blockchain, we create a new block with a message and a previous block. That's where the mining is actually happening. And again, I want to validate my blockchain. So at some point with the Gossip protocol, we are going to send our blockchain all over the place. So when I receive a blockchain from a node, I want to be sure that the blockchain is actually valid. And doing that is really easy. I'm iterating over all the blocks. I'm checking if the block is actually valid. If that's not the case, the blockchain is not valid. And then I want to check that the previous hash, the hash of the previous block is actually the same as the previous hash of the current block. If that's the case, then the blockchain is valid. Right? So here I've created a small blockchain with the Genesis block. Then I'm adding 2 more blocks, and I'm printing the blockchain and trying to see if the blockchain is valid. So if we run that, you can see that I have the first block, no previous hash. You have the nonce, you have the message, the hash with 4 zeros here. Then we have a second block. You can see the previous hash is actually the hash of the previous block. And then we compute the hash with a nonce, and so on. Right? So that's a blockchain. Now, if I want to shuffle the blocks, so here I'm trying to move the first and the second block, it's false. The blockchain is not valid anymore because the previous hash is not the right one. So now we have a blockchain where when we want to add a transaction, I have sent a coin to Bob. I need to add that information into the blockchain. I'm going to do some work. And then when I'm doing the same with Alice, I need to compute the same thing again. But if you think about it, you can probably fork the blockchain, right? For block number 2, I can compute 2 different nodes very easily and send the nodes in a network. So we still have a problem with the double spend issue. We can still double spend the coin, so we are not there yet. So we need something more to make it work the way we need. And the way we can do that is, and now you're going to understand why we need to spend CPU time to actually mine blocks. The way it works is that if there is someone wants to hack the blockchain, so he's going to fork the blockchain and adding some false information, right? But the network, we are transacting all the time, so we are adding blocks all the time, mining new blocks all the time. So if someone wants to fork, at some point we need to decide which chain is actually the right one. And the rule is very simple. Always take the longest chain. And that makes sense. The longest chain is the chain where the most work happened, which means that if someone wants to fork the blockchain, it needs to have more CPU power than everybody else. So it needs to control more than 50% of the computational power of the network, which should not be possible. or at least it was what we thought about. But right now, that's not the case anymore, because you can't mine Bitcoin anymore on your laptop. You need specific hardware, which means that only a few, I think it's something like 15 different Chinese companies, they own more than 80% of the power in the network. And if they can get together and having enough power, more than 50% of the power, then they can change the blockchain the way they want, just because of the longest chain rule. And that's why in the Bitcoin world, you need to wait. And the recommendation is to wait for at least 6 blocks, 6 new blocks after the block where your transaction is in, to be sure that the transaction is final. Because we think that after 6 blocks, the CPU time needed to actually fork the blockchain or change a node and then recompute all the blocks after that is almost impossible. But that's just, it's not a hard guarantee. It's just a probabilistic guarantee, right? Okay, I think we have all we need to actually create our cryptocurrency in PHP now. That's the final piece of code. The block is almost the same as before. The main difference now is that we don't have a message, we have a transaction. And a transaction is from, so who is going to send the money? That's the public key of the sender. Then we have the public key of the receiver, the amount of money, and the private key of the sender. And as you can see, we do not store the private key. The private key is only used when we create a transaction to actually create a signature. And the signature is the encryption of the message, and the message is the concatenation of from, to, an amount. And we are storing also the information about who is sending money to who. Okay, and then we want to be able to check if a transaction is valid. It is valid if there is no from. That's the first transaction when we create the money. And then it's valid if the signature is actually valid. Right? That's where we are checking with the signature that everything is fine. So we have the public key, we have the signature, which is the encryption of the message, and the origin message. Okay, so going back to the block. So a block is a transaction and a previous block, like before. And create genesis is where you create the very first block, and the first transaction is from nobody to the creator of the blockchain with a given amount of money, and we have the private key. And the mining algorithm is exactly the same as before. And the isValid method is, we need that the transaction is valid first, but we also need that the proof of work is actually doing the right thing, so the nonce is actually the right one with the number of zeros. Then we have the blockchain. The blockchain is, again, just a list of blocks. Everything is the same. We are adding a transaction instead of a message. And then, and that's the most important thing here, we need to be sure that the blockchain is valid. So for each block, we check that the block is valid and that the previous block hash is actually the previous hash of the current block. And we also need to check that the spans are valid. We don't want someone to go under 0, of course. To do that, and remember, we are only storing transactions. We do not have balances anywhere, so we need to compute that. We are computing the balances here, and when we check if everything is okay, if there is one amount that is less than 0, then the blockchain is not valid. And when I'm going to send you a blockchain like that, you're going to refuse that because it's not valid. And there's no way you can forge that because of the encryption and the keys. And now we need to communicate together, so there is, again, the same gossip protocol. And basically, we are going still to communicate with the peers. we are sending to the peer our state. So the state is really, so the state is really just the blockchain and the peers we are working with. That's all. So we are going to gossip with our peers. They are going to send their state, and we are going to update our state based on their state. And that's the most interesting part here, how we do that. How can we do that? So first, if we do have a blockchain, we are going to update our blockchain. If we do not have a blockchain, then we are going to accept the blockchain from the peer. That's when we actually create the node for the first time. And the blockchain, the update method here, the first one is the longest rule here. So if the peer blockchain has less nodes than ours, we just got it, right? We only consider longer chains. Then we validate the blockchain. If it's not valid, we just don't do anything. And then really simply, if it is longer and valid, then we accept it, right? And just because of everything we've just talked about, we can be sure that all the information in the blockchain is actually valid. Okay, let's do some demonstration here. No, not the right one. Fabcoin. Okay, so I have a user, that's me again. And here I have a script, which is exactly, the script is exactly the same as before. We have a user and we have a peer to connect to. And we have a PHP web server here. And then this is the service doing the gossip protocol. Okay, so I've just started the network. So I have a million Fabcoins here. And you can see the blockchain at the bottom of the screen. Let's make it a bit bigger. Okay, so I just have one transaction. And you can see here that I have 4 zeros for the hash. Let's create another node connected to the first one. They start gossiping together, as you can see, and let's start another one. Okay, so we have 3 different nodes in the network, and then I want to transfer some money from Fabian to Ellen, for instance. And you can see that it propagates on the network. And you can check that the blockchain is actually valid. You can see all the transactions, and we compute the balances at the top of the screen. Now, if I try to send a lot of money to my wife, money I don't have, that won't work because the blockchain is not valid. So nobody is going to accept my blockchain. Even if it is longer, it's not valid, so we don't care. And if there is a double spend at some point, if there is a fork, and it happens all the time on the Bitcoin blockchain, at some point, eventually, one is going to be longer than the other one. So we are going to reach a consensus just by waiting. And that's why time is very important in the Bitcoin protocol. That's why the claim that sending Bitcoins is much faster than transferring money from a bank, that doesn't work because in the protocol, there is this notion that we need to slow things down to reach a consensus. That's something very important. And of course, I can, go down and I can join again, and it's going to do the right thing. Okay, so it was a very quick introduction to cryptocurrencies and the blockchain. We have not talked about everything here, just about the core concepts, but hopefully you better understand how that works and how it works behind the scenes. The reality in Bitcoin is a bit different. For instance, in a block, you have more than one transaction, of course. We haven't talked about fees or rewards because, of course, a miner is doing some work because he has a reward. If not, that's not that interesting. We have not talked about things like replay protection, for instance, Merkle trees, like clients, because of course on my phone I don't have to have all the information of the blockchain. So there is more than that. But hopefully you have a better understanding now, and you can read the white paper. It's quite interesting. In the template for DrupalCon, there is a slide where you need to put a quote. So that's a quote from me. Whatever. And of course, if you are into cryptocurrencies and if you want to create a cryptocurrency, then a blockchain might make sense. Oh, I haven't talked also about Ethereum. So the possibility to have a virtual machine embedded into the blockchain, which is yet something else. But yeah, that's another story. I think I'm running out of time here. So thank you very much. I think if you have any questions, you can come after the talk to me. Très mauvais. Ça, il faut le parler.
Because you know you started with this one user and you only given him a transaction. So what if you wanted to add another user? Is that going to be labeled as a transaction, or how does that work?
No. Basically, a new user is a public key. So if you don't have any transactions, it's not stored anywhere. Just because you have a node, you can get all the information from the blockchain, and the first time you're going to have a transaction, then your public key is going to be part of the blockchain, but not before. So there is no, and that's something